We are all familiar with the concept of waves. When something emits waves as vibrations, they travel through the air. We perceive these waves as sound. To visualize sound waves emitting from a stationary object, let's say this dot is the object emitting sound, and these circles are the individual sound waves with a visible wavelength. This is a simplified representation of real sound waves, which would normally be spherical in shape. Let's say the observer is this green line. What the observer perceives are vibrations that are spaced out evenly and at a certain frequency, which can be calculated simply with the number of periods per second. The frequency determines how highly pitched the sound is, and the distance between you and the source determines the intensity or loudness of the wave. What happens when the source of the sound moves towards the observer? As the source travels in the direction of the sound waves, it gains ground somewhat on the waves that it has produced, meaning that the next wave it produces would be closer to the previous sound wave in the direction that it is moving, and further away from the previous sound wave in the opposite direction of where it's moving. The frequency and intensity of the sound remains the same for the source, but the perceived frequency and intensity shall change, with the frequency being uniformly higher if the source is moving towards you, and the intensity increasing as the source is moving towards you. The opposite will be true if the source is moving away from you. This, of course, is the Doppler effect. What does the Doppler effect have to do with sonic booms? The frequency of a sound wave from a source moving towards an observer that is perceived by the observer can be described by this equation. We can see that as the velocity of the source approaches the velocity of sound, the perceived frequency will increase and approach infinity. Therefore, if a sound-emitting object moves at exactly the speed of sound, or Mach 1, the perceived frequency will be infinite, meaning that you are receiving all the waves created by the source at once. We can see this happening in this simulation. Because the object is moving at the speed of sound, it travels along at exactly the same speed as the sound wave itself, while simultaneously creating more sound waves that overlap with and travel along with the source and the rest of the waves. Because of constructive interference, these waves overlap and amplify each other, with an intensity that is far beyond what one would normally hear if the object was subsonic. You will experience this as a sonic boom, a large booming sound, and this will happen the moment the object passes you. What if the object is moving faster than the speed of sound? Looking at the Doppler effect equation, we can tell that as the velocity of the source exceeds the velocity of sound, it will produce a negative frequency that decreases as the velocity of the source goes up. This means that the sound waves actually lag behind the source as the source itself outspeeds the sound it creates. This leads to a very interesting diagram showcasing this phenomenon, where the sound waves emitted form a cone trailing the source. As you can see, the edge of the cone also has constructive interference as the waves overlap each other, and that is the region where the sonic boom can be perceived. Strangely enough, based on the Doppler effect equation, the faster the source moves as a supersonic entity, the lower the frequency of the sound waves produced. So the sonic boom produced is not as intense. We can see this by looking at these simulations here. What are some examples of sonic booms outside of the theoretical sense? The most obvious example would be supersonic aircraft. For a plane traveling at supersonic speed, the conical sound trail emitted from the plane would be where the boom could be heard. Depending on the distance between the plane and the ground, the plane could have passed many meters ahead of the observer before they can perceive the sonic boom, as can be seen with this diagram. Another example would be the crack of a bullwhip. As you flick a whip, you create a transverse wave that travels along the length of the whip. A bullwhip decreases in width the further along its length you go, decreasing the linear density of the whip. Therefore, the velocity of the wave increases dramatically as the wave travels, where the wave can go as far as being supersonic, creating a sonic boom which is heard as the crack of a whip that we are familiar with.